Okay, welcome back. This is section 4.4. We're going to talk about some rational exponents. In this video, we're going to use the properties of exponents to convert between rational and radical and exponential form. We're also going to apply the properties of exponents to both rational and radical expressions. And we're also going to explain how the rational exponent properties are related to the properties of exponents that you already know about. So, up until this point, we have talked about the radical sign and the radicand and an index, and we even have powers within that radical sign. We can convert this radical sign into what we call a rational exponent, and a rational exponent is an exponent that's in the form of a fraction. So what that means is the square root of x is really x to the 1/2 power. The numerator is the power that you see inside the radical, or whatever power it's raised to. You can also see it written as the b root of x to the a, so that's the same. Okay, b is the root, so the denominator of the fraction will be the root or index, of the radical expression. And then, of course, you have the base, which is the part of the radicand that is the base of the power. Okay, so let's do a couple examples. So if we want to write these in exponential form, we have our index, which is 3 here, so that's going to be the denominator of our rational exponent. So we have x to the 12 over 3 times y to the 9 over 3 times z to the 6 over 3. And now we can reduce. 12 divided by 3 is 4, so x to the 4th. Y, 9 over 3 is to the 3rd. Z, 6 divided by 3 is 2. And there's our answer. It's an even index, so we don't have to worry about absolute values. Here we have 5 as the index, so that's going to be the denominator in our rational exponents. So we have a to the 10 over 5 times b to the 5 over 5. And since c doesn't have anything, it's assumed that it's a 1, so c to the 1 over 5. And that reduces 10 divided by 5 is 2. 5 divided by 5 is 1, and 1 divided by 5 is just 1/5. Okay, I want you to try this. Pause the video. Welcome back. Here's your answer, and we're going to move on. Okay, so if I want to write this in radical form, I'm going to look at the numerator is my power, and the denominator is my root. So this is the 6th root of x to the 1st power, so just x. If I want to write this in exponential form, same thing. So 4 is my index, so that's going to be my denominator. 2 is my power, so it's z to the 2/4. 2/4 is 1/2, so z to the 1/2. Go ahead and try those. Okay, welcome back. Here are your answers. Pause if you want to review. Okay, so what if we want to evaluate? Well, we can use the properties we just talked about. We know that x to the -1 is 1 over, and then this would be 81 to the 1/4. Well, 81 to the 1/4 is 1 over the 4th root of 81. So can we write 81 as something to a 4th power? And in fact, 3 to the 4th is 81. So we want the 4th root of 3 to the 4th, which is just 3, so that answer is 1 over 3. We want to do the same thing here, so we're going to write this as the cube root of 216 squared. Well, the cube root of 216 can be rewritten as 6 cubed all squared. And so that would be the same thing as the cube root of 6 to the 6th, which is the same thing as 6 to the 6 over 3, which is the same thing as 6 squared, which is 36. Okay, go ahead and try this. Okay, welcome back. Here are the answers. Make sure you pause if you want to review. Okay, so take a moment to read this. Okay, so in this problem, it talks about approximating a period in Earth years. And the question specifically asks us how many Earth years. So we know we're going to solve for P. So in order to solve for P, we need the distance. And when we look at the problem, it doesn't give us anything about the distance, but over here, we have the distance right here. It says Mars is 1.5 AU from the sun. So let's go ahead and plug that in. So to find P, we need to find 1.52 raised to the 3 halves, which is the square root of 1.52 cubed. That's the square root cubed. And so the square root of 1.52 is approximately 1.233. And so when we cube that, we get approximately 1.87 years. Okay, so take a moment. I want you to record these properties of rational exponents in your notes to make sure that you understand them. Okay, so let's use those properties. If we want to simplify this expression, for example, so we have the same base, which means we're going to add the exponents. So a to the 2/7 plus 4/7 is a to the 6/7. And there's the simplest form. If we want to do b to the -5/6, well, a negative exponent tells us that we're going to do 1 over b to the 5/6. But now we have a fractional exponent in the denominator, and we need to rationalize that. That's the same as having a radical in the denominator, and we don't want that. So we need a integer exponent down here. And so that means that the next integer exponent would be 1, right? So 6/6. So if we could somehow add 1/6 to this, then we would get the 6/6 that we need. And in fact, if we multiplied by b to the 1/6, we would get our b to the 6/6, which would give us the single b that we want. If we do that to the denominator, though, we need to do that to the numerator, so that way we're not changing the value of the function. And so we end up with 1 times b to the 1/6. And so b to the 6/6 is just b. So now we have b to the 1/6 divided by b. Okay, go ahead and try those. Okay, welcome back. Here are your answers. Go ahead and review those. Okay, so in general, we say that a radical expression is simplified as long as the index n is as small as possible. And so that converts to exponential functions to say that the fraction is reduced. The radicand contains no factors other than 1 that are to the nth power of an integer or polynomial. Again, that involves reducing the fraction in the exponent. The radicand contains no fractions. So that means that our base of our exponent is going to contain no fractions. No radicals appear in the denominator, so that's going to mean that there are no fractional exponents in the denominator either. Okay, so if we want to simplify this expression, we can start by dealing with the negative exponent and writing 2.5 as a fraction. So we're going to do 1 over 16 raised to the 2/5 is 5 halves. Okay, so now 1 over 5 halves would be the square root of 16, quantity raised to the 5th power, and 1 over the square root of 16 is 1 over 4 to the 5th, and 4 to the 5th is 1 over 1024. Okay, let's try this next one. So if b is -32 to the 8/10, So that means we're doing negative 32 to the 8 over 10, which 8/10 we can reduce to 4/5. So now we have negative 32 to the 4/5, which means we're doing the 5th root of negative 32 raised to the 4th power. Well, the 5th root of negative 32 is negative 2. So negative 2 raised to the 4th power is going to be 16. Okay, go ahead and take a moment to do those. Welcome back. Here are your answers. Okay, so now what happens if the indices are this different? Well, up until now, we didn't have any way to deal with that. But if we write things as exponents, we might be able to do something about it. So if we do 27 to the 1/4 divided by 3 to the 1/2, we notice that our bases aren't the same. So we still can't do anything. But can we write these so that the bases are the same? Well, 27 is 3 cubed. So if we rewrite 27 as 3 cubed raised to the 1/4 divided by 3 to the 1/2, well, now 3 cubed to the 1/4 would be 3 to the 3/4 over 3 to the 1/2. And now we're dividing with the same base, so we can subtract the exponents. So now we have 3 to the 3/4 minus 1/2. And 3/4 minus 1/2 is the same as 3/4 minus 2/4. And 3/4 minus 2/4 is 1/4, so this would end up being 3 to the 1/4. Let's try that one more time. So here we can write this as 64 to the 1/3 times z to the 6/3. Well, 64 we know is 4 to the 3rd. So if 64 is 4 to the 3rd power raised to the 1/3 power, and z to the 6/3 would be z squared. Well, now we have 4 to the 3/3 z squared, and 4 to the 3/3 is just 4, so now we have 4 z squared. Okay, I want you to go ahead and try those. Welcome back. Go ahead and check your answers. And let's try one more problem. Okay, so here we have a fractional exponent in the denominator. So how do we deal with this? We could switch to radical form, or we can just go ahead and multiply by the conjugate in exponential form. So let's do that. So we're going to do 3x to the 1/2 minus 2. And so we're going to multiply this entire fraction by 3x to the 1/2 minus 2 over 3x to the 1/2 minus 2. So now the numerator becomes x to the 1/2 minus 2 times 3x to the 1/2 minus 2 over 3x to the 1/2 times 3x to the 1/2 is 9x. 3x to the 1/2 times negative 2 is negative 6x to the 1/2. 2 times 3x to the 1/2 is positive 6x to the 1/2, so that's 0. And then 2 times negative 2 is minus 4. And so if we want to simplify this, so that way we don't have any fractional exponents unless we need to, we can go ahead and distribute here. So we have x to the 1/2 times 3x to the 1/2, so that's 3x. Negative 2x to the 1/2. Negative 2 times 3x to the 1/2 is negative 6x to the 1/2 times negative 2 times negative 2 is plus 4 divided by 9x minus 4. And now we can combine like terms. So now we have 3x minus 8x x to the 1/2 plus 4 over 9x minus 4, which you could also write as 3x minus 8 square root of x plus 4 over 9x minus 4. Either of these answers is perfectly correct. Okay, go ahead and try this one. Okay, welcome back. Here's your answer. Okay, so for more examples, go ahead and watch the more examples video. Otherwise, go ahead and complete the 4-4 rational exponents reflection. Up next, we're going to talk about how to solve radical equations.